The platypus, Ornithorhynchus anatinus, a mammal native to eastern Australia, has a reputation for being one of the most strange and fascinating creatures on Earth. They are semi-aquatic, nocturnal, and shy, making them inherently difficult to observe and research in their natural habitat. Platypus movement patterns seem to be influenced by several factors, including age, sex, and time of year. But studies surrounding the detection of the animals have shown highly variable results encompassing these elements. This is likely due to a lack of effective tracking methods that provide robust and accurate movement data. I'm Jenni Irwin.
And I'm Maya Gonzalez.
And we are here today to assess the effectiveness of the methods used to track the movement of platypuses and recommend the one that will be the most effective for obtaining accurate estimates.
When using capture mark recapture to track individual animals, a mark scientists typically use is leg bands. Upon capture, the scientists take note of relevant information such as sex and maturity, then place a stainless steel leg band on the animal. These bands serve as identification and with later capture efforts indicate if any marked platypuses move to different sites from their initial location. This kind of mark potentially stays on the platypus for its lifetime as it is compatible with platypus anatomy. It also shows no evidence for damage or ill effects on the animals. However, recapture rates are consistently low, and the traditional methods of recapture usually require significant effort and many hours in the field.
Passive integrated transponder, or PIT tags, are microchips used to track individual animals. Platypuses are implanted with a radio frequency device that sends identification numbers to antennas that are placed discreetly around study sites and send out electrostatic signals. A big advantage of this method is that the tags don't require batteries, so they can hypothetically last indefinitely. This method produces high detection rates, although it can be limited by short detection distances, being most effective in smaller streams. The method is well suited for animals with high sight fidelity, which adult platypuses exhibit. But one of the platypus's many strange and unique adaptations is the ability to detect electrostatic fields in their environment. So there's actually evidence that they can sense the antennas around them, and it's been observed to affect their behavior, including movement. Furthermore, receiving antennas can also be moved or damaged if placed in fast-flowing water and not secured properly.
The last tracking technique we'll discuss is acoustic tags, a form of telemetry. With this method, an implanted device tracks individual animals using an acoustic transmitter. Upon capture, platypuses are anesthetized and a tag is inserted into their abdominal cavity. The tags emit a pulse of sound at designated intervals, which are then picked up by hydrophone receivers, which are underwater microphones that can triangulate platypus locations over large distances and study areas. Using hydrophones to receive and store data is a relatively convenient method because data can be collected from the receivers through Bluetooth and they can store over 1 million detection events, providing both small and large-scale geographic data depending on their locations. But the tags are limited by battery life, lasting up to 13 months with the correct optimization, but only around 6.5 with the default settings. The tags do not cause any harm if implanted correctly, but the implantation process is pretty invasive and can cause short-term discomfort or pain or medium-term effects such as inflammation. Researchers must also avoid tagging lactating females as it can be risky to their health. But these tags can give researchers additional information about physiology and circadian activity to monitor the health of platypuses that do become tagged.
While all of the mentioned techniques provide adequate data, we believe acoustic tags are the most effective method for providing movement data. They provide around-the-clock geographic information that can be categorized into multiple demographics such as age or sex. To address this method's main downfall, which is battery limiting study lengths, scientists could optimize battery usage by lowering the pulse rate of the tags and limiting the active time to when platypuses are known to move. As seen in the table, decreasing the pulse rate for a commonly used model, the V74L, can more than double the tag's battery life to a period of over 1 year. All other concerns, such as the short-term discomfort and inflammation of implantation sites, are minor issues that have not been shown to affect the behavior of sampled platypuses or affect collected data. In conclusion, programming battery trade-offs into the acoustic tag technique can provide scientists with the best chance at a long-term, robust study on platypus movement.
We would like to take this moment to acknowledge the sources that have guided our research and thank you to our viewers for attending this presentation. We encourage you to use the comment section on this video to voice any questions or feedback you may have.
Thank you.